For my project, I decided to research the geologic history of the Patagonian Andes. This is a really cool region geologically for a bunch of reasons. There are a lot of really unique rock formations like these ones, and a huge variety of different ecosystems within the Patagonia region. It also has a rare triple junction where three faults meet, and contains the second largest ice sheet outside of the poles, which is really crucial to keep tabs on for climate change. So, just for context, Patagonia is the southernmost region of South America in Chile and Argentina, and the Andes Mountains are on the western side of Patagonia, while the east is generally an arid grassland. And the Patagonian Andes lie right along the edge of the South American plate, where it meets the Nazca and Antarctic plates. The South American plate is moving southward, while the boundary between the Nazca and Antarctic plates is actually a mid-ocean spreading ridge. So those two plates are spreading apart from each other and actively subducting underneath South America. But how did we end up here? Well, if we time travel back to the early Cambrian period, this is where our story begins. At this time, the continents were all pressed together in the Gondwana supercontinent, and we have South America right here. And the land that is now the southern Andes was along the southwestern edge, which rifted away from the rest of Gondwana. And there are also these two smaller microcontinents, the North Patagonian Massif and the Deseado Massif. So these two massifs are plateaus of thicker continental crust surrounded by thinner sedimentary basins. And so these two main massifs now make up the basement rocks in this region. Throughout the Paleozoic and early Mesozoic, this region was operating in an extensional tectonic system, which means that these plates were spreading apart. From this time period, we can identify a few distinct geologic layers that make up the basement rock. First, we have a layer deposited during the Paleozoic period here, mostly made up of granites and gneisses, pretty high-grade metamorphic rocks from being buried under so much other material. Then here, from the Jurassic period, we have a layer of marine sediment and volcanic rock. Because of this, we can infer that during the Jurassic, the southern Andes were underwater, where marine sediment could be deposited. Then, during the Cretaceous period, we have what is maybe the defining characteristic for the southern Andes, the Patagonian batholith. A batholith is a large igneous intrusion that forms when a huge mass of magma cools underneath the land's surface. The Patagonian batholith is consistent throughout the entire southern Andes and is visible in places like Torres del Paine National Park. Then, in the Cretaceous period, it switched from an extensional tectonic system to a compressional system, which essentially means that the mid-ocean ridges on either side were accelerating and the western plate began to subduct, creating the Andean fold and thrust belt. This is also when we begin to see a geographical boundary emerge between the northern Andes, also known as the Principal Cordillera, and the southern Andes, the Patagonian Cordillera. We can also split the southern Andes up into three regions: north, central, and south. In the northern Patagonian Andes, we have those same basement rock layers, the Paleozoic granites, the Jurassic marine sediment, and the Patagonian batholith. But on top of that, we also find a thick layer of volcanic and marine sediment from the Paleogene that's present on both the western and eastern sides of the Andes. We know then that this area must have been near sea level and has been periodically flooded by the Pacific Ocean. Now, the central Patagonian Andes have nearly the same geology as the northern section, but with a few key differences. We don't have those Paleogene volcanic and marine rocks on both sides of the Andes now. Instead, we have Paleogene and Neogene continental sediments on the eastern side. This means that in this section, the Andes were high enough above sea level to block the Pacific Ocean from reaching the eastern side. In the southern Patagonian Andes, we're actually able to see this Paleozoic basement along the foothills of the mountains. It's that rust-colored section there, which is super cool. But unlike sections further north, this basement is made up of mostly sedimentary rock, not volcanic. Instead, with that sedimentary rock, we start seeing something that looks a little bit like this. We're seeing these very thick layers of marine clastic sediments interbedded with thin limestone, and this tells us that there was a changing depth of marine environments at this time. So we're having multiple Pacific spillovers, and so the sediment supply is kind of switching back and forth between biogenic and clastic. So the times that we have clastic sediment must have been pretty close to the Pacific shoreline at that time. And when we have these limestones, we can assume that it was in deeper water, and this is during the Paleogene. We are getting these sort of spillover events. As the Andes continued to uplift, a rain shadow formed, which is still very present and important in Patagonian ecosystems and geology today. Water would evaporate up off the Pacific, move onshore, and then the mountains would trap all the precipitation on the western side. What we begin to see is that precipitation eroding away super strongly on the west. And today we can see lots of archipelagos, fjords, and channels, and we can also see the Patagonian batholith exposed on that western side. And as opposed to those really lush environments on the west, the eastern side is getting desertified from the lack of precipitation, and it developed into something called a steppe environment, which is a dry grassland. No forests, flatter, a lot more shrubby. But in addition to the change of environment, on this eastern side we also have a much more complete sedimentary record. With less water to drive erosion, more sediment is able to stay in place, and we get a really consistent geologic record here. During the last glacial maximum, the Patagonian ice sheet covered this entire area here, and those two little blue sections are the North and South Patagonian ice fields. Although it doesn't look like much compared to what it once was, this existing section is actually the second largest continuous ice mass outside of the polar regions. As the ice sheet receded after the Pleistocene, temperate rainforests grew in former glacial areas. We can see the remnants of the ice sheet in these dramatic glacial valleys and glacial lakes, and plenty of incredible temperate glaciers remain in the southern Andes today. During this last glacial maximum, Patagonian volcanoes were experiencing really frequent and explosive eruptions, and this is because the weight of such a massive ice sheet put a lot of pressure on the volcano system underground, and magma was forced out really explosively. But when the glacier began to recede, there was much less pressure, and so eruptions were a lot less strong and frequent, more like slow lava flows, which creates some incredible rock formations like this. This glacial retreat is also more dramatic because the Patagonian Cordillera has a uniquely high isostatic rebound, which is the amount a land mass rises after it was depressed by the weight of an ice sheet. So after the ice sheets retreated, the southern Andes began to grow even faster than they did before, because this area has a much hotter upper mantle thanks to the triple junction. The Chile Triple Junction is the only place on Earth where there's an actively spreading mid-ocean ridge being subducted underneath a continent. That's amazing in and of itself, and it's a really cool place for geologists to study how different types of plate boundaries interact. But also, the Nazca Antarctic plate boundary in the middle there, or the Chile Rise, is not approaching the South American plate head-on. Because of the angle of the Chile Rise, the age of material being subducted is anywhere from 0 to 25 million years old. Subduction zones usually heat up the upper mantle, but that spot where the brand new oceanic crust is immediately subducted under continental crust is about as hot as you can get in a subduction zone. Patagonia has been and will continue to be an extremely active area tectonically as that triple junction continues to subduct and the Andes keep growing taller. I hope you all found the geologic history as interesting as I do and that you enjoyed learning about Patagonia. Thanks so much for watching.